This exercise, I want to find an exact answer for the tangent of 9 degrees. I don't want a decimal approximation. I don't want a small angle approximation. I want an exact answer. I want an expression that gives me a solution to the infinitieth decimal place. So that's what we're going to look at doing today. To start with, we're going to take as given the 1872-90 Special Triangle Theorem. That's this triangle in orange here. It has 1872 and 90 degree angles, and these are the side measures. Now this is a theorem you probably didn't learn in high school. It takes a little bit to derive, but can be done from the regular pentagon. I don't want to go too in depth with this, but given a regular pentagon with side measure of 1, that's the blue, the diagonals are in orange here, you can derive 2 special triangles, one of them in this area here and one of them right here. You end up with the 36-54-90 triangle, and you also get the 1872-90 triangle, which is the one that we're going to start with today. Now this one's up on end here. So the one in the other picture that I had is just rotated. That's a simple geometric transformation. One fun thing about this derivation and the regular pentagon is it involves the number phi. So those that like the golden ratio, that shows up in this derivation. The reason that we chose this particular special triangle theorem to find the tangent of 9 degrees is because I've already derived this, and we have 18 degrees here. Half of 18 is 9. So we're going to use a theorem that you probably have learned in high school, the Triangle Angle Bisector Theorem, to help us derive the triangle that we are looking for that will give us the tangent of 9 degrees exactly. And so the first thing we're going to do is replicating this orange triangle over here. I want to cut this angle, which is 18 degrees, in half. So I want to create a bisector through here. That's going to split this opposite side. The theorem does not say that this side is split in exactly 2 congruent pieces. There are multiple ratios that this side could be cut into. What the theorem does tell us is that given that this angle is cut into exactly 2 congruent angles, we have a proportionality. Alright, so I've bisected this angle, so I have 9 degrees here using the fact that interior to any triangle is 180 degrees, we're able to determine that this angle here is 81 degrees. I've stated the Triangle Angle Bisector Theorem as it is basically stated in the textbook that I teach from. This is not really the form that I personally want to use. I'm going to use an equivalent form, and this is just manipulation of proportions and fractions. That I want to use the ratio of AB to AC is equivalent to BD to DC. And I've gone ahead and labeled this triangle so that all these letters are going to match up here. So I have this angle that we bisected is labeled A over here at this vertice. We had this vertice labeled as B and C here, and then this intersection point is labeled as point D. So we're looking at AB, which is this side, to AC, which is this opposite side, to BD and DC. So these opposite sides are in proportion to each other. These sides that were originally one side are in proportion to each other, and this is the form that I want to use. So I want to make some substitutions in here now. And these two sides we don't know the measures of. The side that we're really interested in is this side DC. So I'm going to assign another variable in here. I want to let DC equal y, so that BD can be represented in respect to DC. So the entire side length here for BC is this. So it's this number minus this number. So BD is going to be equal to this distance minus whatever the value of y is. So these things are going to be substituted into here along with the other values that we know, this value here and this value. With our substitutions put in for this proportionality, we have this. So if you work through the algebra here, you have y is equal to this term. This term can be simplified a little bit, and you can rewrite this so that you can eliminate the denominator here. Alright, so here's where we are. We have this triangle, 9 degrees, 81 degrees, and 90 degrees. We have this side length here, and this side length here. At this point, we technically have enough information to find the tangent of 9 degrees. It's the ratio of opposite over adjacent, so we have the opposite over adjacent. If you want to find this side AD, which you certainly can, you are going to apply the Pythagorean theorem, side A and side B. This will be side C, so we have this squared plus this squared is going to equal this squared. And so take the square root of that and you will have this missing term. It can be done, certainly. It doesn't look the prettiest, but it will be an exact answer. And so you will have another special triangle theorem, the 98190 theorem. But let's go ahead and finish out the original question here that we were asked. Find 9 degrees here. And this triangle that I created here is this triangle down here. So we are going to do opposite over adjacent. So we have tangent of 9 degrees is equal to the opposite. So this term divided by this term down here. We have this entire thing in the numerator, this in the denominator. This is a reducible fraction. So if we look at this, this is really going to be multiplied by this denominator here, and then we have the same term that's going to be in numerator and denominator, and so this is going to reduce. This is our final answer. And so this is an exact valuation for the tangent of 9 degrees. For those of you that like a little bit of completeness, I've gone ahead and calculated out the missing side length from our triangle, and then I divided all sides by this term so that I had a triangle with a side length of 1. This is allowed by similar triangles. I've just scaled the triangle so that I have at least one side length of 1, and so I have this term, which is the tangent of 9 degrees that we just found, and then I have this as my hypotenuse. Some of you may be really good with manipulating these types of expressions and can make this look better than I have. Here, this is the 98190 Special Triangle Theorem. And that ends this exercise. Cheerful calculating.